This is Lab 2, Motion of a Falling Object. In this lab, I took a video of a ball dropping from midair and analyzed it in Tracker. Then I used Newton's second law to include the acceleration caused by the Earth's gravitational force in Python. I also added drag force onto the computational model to see if it helped predict the real position of the ball in the experiment. The data taken from all three computational models were compared by graphing the position versus time points to see which model fit the experiment. Different formulas are used to analyze the velocity and position of the ball. We find that F net is equal to 0 because of Earth's gravitational force. Because there's acceleration, we can now show that Vf is not equal to Vi. Drag works against the object's motion and opposes the gravitational force. With this, we add them together to get the final net force. My video was analyzed through Tracker to find the position and time data. The origin of the axes was put at the center of the ball, causing it to move in the negative y direction when dropped. With the position and time points from Tracker, I was able to create a computational model that best reflects the experimental model. The different codes used in Python were drag and weight. Drag is found as negative b times velocity squared, and weight is found as negative mg times j hat. The position vector started at 0, 0, 0 because the origin is set at the center of the ball. First, I created a computational model without drag force to see if it fit the experimental model. Because drag is negative b times velocity squared, I set b equal to 0 to make drag force unaccountable. Arrows were added to the computational models to signify the gravitational and drag force. The gravitational force is the yellow arrow going in the negative y direction, and the blue arrow is the drag force going in the positive y direction. The blue arrow is only present if the drag force was added to the model, so there is no arrow in the first run. The arrow scale was found by dividing 2 by the weight, mass times 9.8. As you can see, when running, there is no drag force implicated, and the final position of the model is not the same of the experimental model. Without drag force, the model is predicted to go further than the actual experiment, as you can see of those two numbers. The next computational model was designed to include drag by finding the correct number for b. In the previous run, b was equal to 0, getting rid of the drag force. This time, I used a sequence of trial and error of running the program and changing b until the final positions were the same. b was found as 0.01. You can see as the program is run, the drag force was added as there is a blue arrow going the opposite direction of the gravitational force. Because drag force was added to the model did not overpredict the position of the ball and oppose the gravitational force, therefore matching the final position of the experimental model. I graphed the data of the three models into a position versus time graph. There are differences between the computational model with no drag force and experimental model, but the computational model with drag force ends in the same spot as the experimental model. This is because, like I've said before, of the drag force opposing the gravitational force, making the model not overpredict the final position. I created a velocity versus time graph of each of the models, dividing the positions by the times. These lines show that there will not be any terminal velocity. The lines all have a straight negative slope, not horizontal, signifying that there is a constant acceleration. If the ball were to be thrown down instead of starting from rest, the ball would have a different terminal velocity. The ball's initial velocity wouldn't be 0, therefore it would not start at the origin but further down the y-axis. In conclusion, we found that as the tennis ball dropped from rest, the two known forces acting on it were Earth's gravitational force and drag force. Without the drag force, the computational model overpredicted the actual final position of the ball, and it proves that drag force has to be accounted for. Because F net was not equal to 0, the final velocity does not equal the initial velocity and instead showed constant acceleration.